x. All right, let me do some basic review here. Find vertical asymptotes, horizontal asymptotes, holes, and x-intercepts for rational functions. To find vertical asymptotes, we're just going to set the denominator factor equal to 0 and solve for x. We want to make sure that the factors do not cancel with the numerator. If factors do cancel, that's going to indicate there's a hole. If there's a hole, that's something else. So to find holes in the graph, we identify factors that can match and cancel out between numerator and denominator. Then we set those factors equal to 0 and solve for x. That will give us the x value location of the hole. And if we want to find the y value location of the hole, we can plug that x value into the reduced expression without the hole, and that will get us the y value of that hole. To find horizontal asymptotes, this is going to be end behavior. We compare degrees between numerator and denominator. If the numerator and denominator have the same degree, then the horizontal asymptote is just the ratio of the leading coefficients. If the numerator is less than the denominator, meaning the denominator is greater, then the horizontal asymptote is always at y equals 0. And if my numerator is greater than denominator, then there is no horizontal asymptote. The graph is headed towards either positive or negative infinity on both sides as end behavior. Okay, so for number 9, we see there are no factors that cancel out. So we know there's no hole. But the 3 minus x in the denominator is telling us that there is a vertical asymptote. So there's a vertical asymptote at x equals 3. We just simply set that 3 minus x equal to 0. And so we know at the very least, the graph is going to look something like this. Okay, no holes. Vertical asymptote at x equals 3. Horizontal asymptote. So this is where we compare degrees. The numerator and denominator, they both share a degree of 1. So we can just look at the leading coefficient. This is a positive 1 in front of x. This is a negative 1 in front of x. So 1 over negative 1 is negative 1. So my horizontal asymptote is going to be at y equals negative 1. The nice thing about drawing the asymptotes is it kind of gives us boundaries of where our graph is going to live. It allows us to sketch a graph without having to plot every single point, because we know the graph is going to hug along those asymptotes. Makes it easier to sketch our graph. Okay, there's 2 more points that I think are easy for us to know and review are x-intercepts and y-intercepts. So to find x-intercept, you're going to replace your y with 0 or your f of x with 0, and then solve for x. Zoom in here. But if it's clear that it is just the, yeah, if there's a numerator and denominator, then in other words, you're just going to set the numerator equal to 0. We don't set the denominator equal to 0 because if we do, then we're looking for either whole or asymptotes. So in other words, set the numerator equal to 0. So my x-intercept is at -2, 0. That gives us a good anchor point for a point on the graph. And then to find a y-intercept, I'm just going to replace every x with 0. So if I replace all the x's with 0, I get 0 plus 2 over 3 minus 0. I get 2 over 3. So y equals 2/3. So my y-intercept, let me just create a space for that. Y-intercept is at 0, negative, or sorry, positive 2/3. So estimation, I'm going to estimate it to be somewhere around here. So we know our graph is going to go through those 2 points, and it's going to eventually hug along those asymptotes. So we know there's a top portion that's going to look something like this. And here, if I just plug in any point, I know my graph is either going to be in this region or this region. If I plug in like 5, 6, or 7, anywhere here, I'm going to get something that is in the negative. And this negative is going to be more clearly down here. So my graph is going to go along here. Let's see. Let's try number 11. Oh, yeah. So the way we find horizontal asymptote, we compare the degree between numerator and denominator. So you see how the numerator degree has a degree of 1. Denominator is also a degree of 1. So if the degrees match, then the horizontal asymptote is just the ratio of the leading coefficient. So here it's a 1x over a negative 1x. So it's just going to be 1 over negative 1, which is negative 1. Okay, we'll skip 10. Have you guys try that on your own later. Let's try number 11. Let's factor everything first. Otherwise, it's tough to know exactly what stays and what doesn't stay in the denominator. So I'm going to just factor everything out. Okay. Whatever cancels out between numerator and denominator is going to tell you that there's a indication of there's a hole. Anything in the denominator that does not cancel out is going to be indication of where there's a vertical asymptote. Anything in the numerator that's left over will be an indication where there is an x-intercept. But in this case, looks like we have 2 holes, 1 vertical asymptote, and we don't have any x-intercepts because there's no leftover x's in the numerator that remains after we cancel these out. So anything that I've canceled out is indicating that a location of the hole. So if I set the x equal to 0, that's just going to be a hole at x equals 0. If I set x minus 2 equal to 0, that also indicates that there's a hole at x equals 2. So we know there are two holes, hole at x equals 0 and x equals 2. The way that you would find, because well, remember a hole is a order pair, right? There is an open circle. So we know the x value of the hole. We don't know the y value of the hole yet. The way you would find the y value of the hole is you create your reduced expression with the holes removed. So there's a 1 left over in the numerator. The denominator just leaves me with x minus 3. And we can plug the 0 and 2 separately into the reduced expression. And that will tell us the y value of that hole. So here, if I plug 0 in for x, 1 over 0 minus 3, that's negative 1/3. So we know there's a hole at 0, negative 1/3. And if I plug 2 in for x, I get 1 over 2 minus 3, which is 1 over negative 1, which is negative 1. And then there's a hole at 2, negative 1. So I'm going to put those order pairs in. Vertical asymptotes. We look at the leftover denominator that did not go away, and that tells us that there's a vertical asymptote there. So if I set the x minus 3 equal to 0, I'll get x equals 3. So there is where my vertical asymptote is. There's no x-intercept because there's no leftover numerator that I can set equal to 0. If I set 1 equal to 0, that's not there's no value to find there. So there's no x-intercept. Horizontal asymptote. Find horizontal asymptote. You're going to go back to your original equation, and you're going to look at the degrees, the highest degree in the numerator and the highest degree in the denominator. So here, if you look at this original function here, which side has a higher degree? Denominator. So if the denominator has higher degree, there is a horizontal asymptote. Where's the horizontal asymptote? Good, y equals 0. Whenever the denominator has a higher degree, your asymptote is always at y equals 0. So
how come there's no x-intercept again?
there is no x-intercept because you know how the previous problem, I could set the numerator equal to 0 and find that x-intercept? Here, my numerator is just a 1. So if I set 1 equal to 0, I'm not going to get anything out of it. And we don't set these equal to 0 because these are holes. So if we remove all the things that are not holes, let's say there was another x plus 3 sitting here, then you would set that equal to 0, and that will be your x-intercept. But in this case, there's no x-intercept. So the graph is never going to cross the x-axis in this graph. Let's see if there's anything else. Y-intercept. So y-intercept is replacing your x's with 0 and solving for y. So if I replace x with 0, I get y equals negative 1/3. So, but the y-intercept is going to be the same thing as the hole. So we're just going to put a hole where the y-intercept would have been. Okay, so here's a sketch of the graph. We have holes. Sorry, let's start with the vertical asymptote at x equals 3. Sorry, x equals, 3. horizontal asymptote at y equals 0. So that's why the graph doesn't have an x-intercept, because there's an asymptote there at y equals 0. No x-intercept. The hole is at -0, -1/3. So I'm just going to estimate where that is. And 2, -1. So even though the graph doesn't exist there, this kind of still helps us graph it, because we know that if there's a hole in the graph is still going to go through those, it's going to pass through those points. So I know my graph is going to kind of hover below the asymptote, and it's going to hug along that vertical asymptote. And if I plug any point to the right of 4 or 3, I'm going to get a positive number, and that's going to indicate it's going to my branch is going to kind of live in this upper region, and I can just follow along the asymptotes to kind of get a rough sketch. Okay, I'll leave 10 and 12 for you guys to do on your own, but the same steps here. Let's go to page 4. Find domain and range. So domain is where your x values exist on the graph, and we can clearly see there are 2 asymptotes that's breaking the graph up. So we know our domain is just going to kind of surround those. It's going to kind of work around those asymptotes. So I can tell by looking at the graph here, I have vertical asymptotes at x equals 1 and x equals -1. So I know those will not be included in my domain. But the graph is going to extend towards negative and positive infinity. So I'm just going to say negative infinity all the way to my first break, which is at -1. And then between -1 and 1, you can do comma or union. And then it's going to pick up again to the right of 1 to infinity. So for range, we're looking at the y values, and we see that it's the horizontal asymptote that's going to kind of break up our range. We see there's a horizontal asymptote at y equals 3. And we're just kind of working around that horizontal asymptote. So here, for range, you're looking from the lowest to the highest y values. And if I look at the lowest y value, it's going to be negative infinity, because the arrow is going to extend all the way down there. So we're going to say from negative infinity. Now this graph is going to hit this, it's going to have a little bit of a vertex. So it's actually going to hit this y value at -2. It actually touches that point. So when we stop at -2, there's going to be a bracket there, because we actually do reach that point. Sorry, +2. That's a +2. And then we skip, there's a bit of a gap, and then we pick up again above 3. So all this is hovering slightly above 3. So we pick up again from y value of 3 all the way to infinity. And then we've already talked about the horizontal and vertical asymptotes. Horizontal asymptote is at y equals 3. Vertical asymptote, x equals 1, and x equals -1. Okay, 15 is pretty straightforward. Let's talk about domains and ranges when there's a hole involved. So number 16, you look at the hole here. The hole is at negative 3, 3. Sorry, my graph's a little grainy here, but there's a hole at negative 3, 3. So if I want to find a domain, my domain is going to work around the x value of the hole, and the range is going to work around the y value of that hole. So domain, we extend from left to right. So the only thing that's breaking the graph up in terms of the x value is there's a hole that's breaking up the domain, and there's also a vertical asymptote that's breaking up the domain. So there's a vertical asymptote at x equals negative 2. So our domain is just going to be working around the negative 2 and the negative 3. In the range, if you look at the range here, there is no horizontal asymptote. So the graph is going to extend from negative infinity all the way to positive infinity. The only thing breaking it up, actually, this hole doesn't break up the range. Why is that?
The graph up to the right goes up to infinity.
Yeah, this graph does extend up. So even though there is a break here, this graph is eventually going to cover the hole here. It will eventually reach that hole. So it's going up very slowly, but eventually will touch this y value. So it looks like initially the hole was going to impact the range, but upon closer observation, we see that that gap will be filled. Yeah, I can use U or commas. Those are all acceptable. Yeah. I just kind of switched it up between my problems here. Okay, go ahead and try 17 and 18, with everything that we've learned, or that we've not learned, but everything that we reviewed, see if you're able to put some of those things together. So try 17 and 18, and then I'll go over those with you. So we know vertical asymptotes comes from the denominator. We're looking for a factor that's going to show us that we can set equal to 0 and get equal to 4. So if you look at part A here, I know there's a 4 sitting here, but if we factored it out, it actually ends up giving us 2 and -2. So actually, the asymptote, vertical asymptote, is actually at 2 and -2, which doesn't meet the condition that we're looking for. Part B, there is an x minus 4 here, but this is not a vertical asymptote. What's happening here? It's a hole because there's a common factor up in the numerator. If there was not an x minus 4 sitting up here, then this would be a good candidate for a vertical asymptote. Here, there's the x plus 1 is telling us there's a vertical asymptote only at x equals -1, which doesn't match that. And so D works because there's an x minus 4 in the denominator that does not cancel out with the numerator. It remains in the denominator. If I set that equal to 0, I would get x equals 4. So answer choice B.
Was that a -7? Yes.
Yeah, sorry, it's graining. X squared minus 7, x plus 12. Try 18. If it helps, factor everything out first, and then it's easier to make your conclusion about what's true about the function. Okay, for 18, I factored everything out first. So x squared minus 5x plus 6 becomes x minus 2 times x minus 3. Denominator, x squared minus 4 becomes x plus 2 times x minus 2. The pairing of the x minus 2 tells us there's a hole at x equals 2. The remaining denominator, x plus 2, tells us there's a vertical asymptote at x equals -2. What does this x minus 3 tell us? I know it's not part of the problem here. Where can we find from that x minus 3? The what? Good. This is where the x-intercept here. So there's an x-intercept at x equals 3. I know it's not part of what they're asking for, but I just wanted to kind of list out all the properties of a function. And if I want to find a horizontal asymptote, I think the best place to look for a horizontal asymptote is not with the factor form, it's with the original function. And what do we do if we want to find horizontal asymptote? What do we compare? Degrees. If the degrees are the same, and they are, we look at the number that's in front, the coefficient in front of that variable. So there's a 1 in front of the x squared. There's a 1 in front of this x squared. So 1 over 1 is 1. So the horizontal asymptote is at y equals 1. So the only one that, let's see, option 1 doesn't work because there's actually a hole at x equals 2. Vertical asymptote at x equals -2, that is true. Horizontal asymptote at y equals 1, that's also true. So answer choice D. Hey, page 5. these are just parent functions of different families of functions that are good to know, just in terms of what they generally look like and how they behave. So I'm going to have you guys copy these down. Yeah. So first up is a linear function. So linear function is a graph is with either just a positive slope or a negative slope. That slope is going to remain constant throughout the entirety of the graph. So a parent function would be y equals x. Domain and range covers all real numbers. Quadratic function. The parent function will be y equals x squared. It could also go sideways, but we're dealing with functions here, so it's either going to have a vertex of a max or a min, but the parent function is just y equals x squared. The domain is all real numbers, but the range would just go from the vertex to infinity. If it's opening down, then it'll go from negative infinity up to the y value of that vertex. A cubic function, y equals x cubed, is the parent function. It kind of has a S shape. The arrows are always pointing in opposite direction, but that also goes for all odd functions. Any odd degree functions, your arrows will be pointing in different infinity directions. And then your even functions, your end behavior, you're always going to have your arrows pointing either both up or both down. Your domain and range would be both all real numbers, just like your linear graph. Next up, reciprocal functions, rational functions. Typically, rational functions have a vertical and horizontal asymptote. So the parent function of this would be 1 over x, y equals 1 over x. We can tell that there, for this parent graph, there is a asymptote at x equals 0 and at y equals 0. The x equals 0 is going to impact your domain. And here, the y equals 0 is going to impact your range. But these rational functions will always kind of have these kind of a branch looking shape to it where the asymptotes are impacting the shape of your graph. Okay, next up, square root function. Typically has a starting point and it curves to the right usually, unless it's a negatives are involved, but this is what the parent square root function will look like. There is a physical starting point for your square root function, and so your domain and range do include a bracket to indicate that it does have a physical starting point. So usually there's brackets involved for both your domain and range. Next up, cube root functions. Cube root functions kind of look like a sideways version of cubic function. Domain and range are both all real numbers, just like cubic functions are.
Cubic function range, is that a plus or?
Negative to positive infinity.
Okay.
Sorry, yeah. Yeah, I didn't need that positive there. Positive infinity, same thing as infinity. Next up, exponential function. Exponential function typically has horizontal asymptote. And so the graph usually starts off flat and then it just it grows really fast. Just like how we see it there. I mean, there's also decay functions, but typically, our most common function that we're going to deal with are e to the x. So just knowing the shape of that it's good to know. Logs are inverse functions of exponential functions, and we're going to talk about this a little bit more. But the idea is that if I were to take exponential function and if I were to flip all the x and y values, I'm going to end up with a graph that looks like a log function. So we're going to talk about that inverse relationship between exponential and log functions, or e to the x and natural log of x. But it's just good to know, basically, what they look like and how they're shaped. And because they are inverses of each other, you can see their domains are also flip versions of each other. Domain of one is the range of the other. Range of one is the domain of the other. And exponential functions has a horizontal asymptote. Log functions have a vertical asymptote. Okay, last up, absolute value functions. Kind of has a V shape to it. A lot of times we can think of absolute value functions as a piecewise function of two linear graphs. So let me include that as well. So absolute value of x is the same as having two linear graphs that has a starting where each has a starting and ending point. So there's a positive slope version of this, which is y equals x, that lives to the right of 0. And then you have a negative x version, a linear graph with negative slope that is living to the left of 0. So sometimes absolute value functions feel a little cumbersome to work with. And so if that's the case, a lot of times it's good to kind of break up an absolute value function just into two line segments and then treat them individually as line segments rather than absolute value function. Okay, 2 more minutes and then we can stop here. So page 7, just going to have you guys copy down some of these notes up here. Transformation of parent functions. So if we take any of the parent functions that we've just talked about on the previous 2 pages, anything that is in parentheses is impacting the graph shifting left or right, but it's always going to be opposite of what you would expect. So for instance, a -3 would be shifting right, meanwhile a +3 would be shifting left. So any addition or subtraction that is within the function is always going to impact your left and right movement. And then the value that's added or subtracted that feels outside the function is going to end up shifting the graph up or down. Any value that's being multiplied in front as a coefficient in front of the function is either going to stretch the graph vertically or it's going to compress the graph vertically. And you want to look to see that coefficient is larger than 1 or greater than 1. If it's greater than 1, it's going to stretch it vertically. If it's less than 1, it's going to compress it vertically. And if you have a negative in front of the function, that's just going to be it'll take that parent function, or take that graph and it'll flip it usually over the x-axis, but it's going to usually be a horizontal reflection. Okay, so real quick here, number 1. So the parent graph for number 1 is x squared. The -3 is going to shift that x squared to the right 3.
Good morning, Bill, students, staff. This is just a friendly reminder that we will be going to homeroom at the conclusion of second period. So students, please report to your homeroom class. Remember, we will be doing that all this week. This is also a reminder, teachers, that please hold your students until we get on the PA system and tell you to release them to their designated spots. Today, during homeroom, 9th grade students will be escorted to the cafeteria by their homeroom teachers, and the seniors will be escorted to the gymnasium by their homeroom teachers. 10th and 11th grade will stay at their homeroom homeroom. So again, at the end of this period, please report to your homeroom class and teachers. Do not send students anywhere until we release them on the PA system. Thank you and have a great rest of your day.
Real quick, your homework is pages 1 through 5, all. I will send you a reminder as well as the key to the packet key, so you can check your answers. And then this whole week, we're just kind of trying to get through packet key, 5E, and then
So this is, we're gonna go over this.
no, but tomorrow I can.
Okay.
Yeah. Just remind me.
Oh. But I think it's probably the only thing.